Hi, my name is Robert Feranek. I'm from Fedevel Academy, and in this video we are going to have a look at a presentation. Presentation! I don't like presentation. They are so boring. Not this one. This presentation, what we are going to speak about, is one of the best presentations what I have seen about electronics and PCB layout topic. And in this video, I'm just going to point out few parts of this presentation which I found very interesting and which I think maybe can be also interesting for you. And if you like it, then you can watch the whole presentation. I highly recommend you to watch this presentation. It's awesome. The presentation is from Altium Live 2018 conference, and the presentation is from Rick Hartley. If you would like to find this presentation, just Google for Altium Live 2018. Click here, look back at Altium Live 2018. Scroll down, click on Speakers, San Diego, Rick Hartley, and click here, watch the presentation. We are going to start with something simple, but very important. So listen carefully.
Opposite situation where with distributed circuits where propagation time is long compared to rise time, then you have a situation where you get a wave that starts at the driver and comes charging down the transmission line. And Eric talked about this yesterday. When it's at the midpoint of the line, you have full voltage and current in the line up to the midpoint, and you have nothing beyond the midpoint. You have no voltage, no current, because all of the energy is distributed through that wave coming down the transmission line.
Why it is so important? What do you think? Why I pick up this from the presentation? Because many people think that everything what is happening in electronic circuits, many people think it's happening instantly, like this. Magic. Yeah? Even when I was starting with electronics, I also thought that everything what is happening in electronic circuits is happening instantly. And then one day I was designing this board with many logic gates, many AND gates and OR gates, and the board didn't work. Or it didn't work as I was expecting. Do you know why? Because not everything is happening instantly. I realized, that was the first time when I realized that when you have, for example, AND gate, then the signal which is coming out of the AND gate is going to be a little bit delayed. It is going to be a little bit later than the signal which is coming inside of the AND gate. Yeah? So this was the first time when I realized that the signal travels through the circuits, the signal travels through the components, and there is some delay. The signal needs some time to travel through your circuit. And when we have a look here, this is a very simple example. Here is an output, here is an input. And when I was starting with electronics, I thought that the signal which is here on the input is always exactly the same as the signal which is here on the output. In reality, the signal or the change of the signal needs to travel from the output to the input. Okay, so in reality, when this signal, when this change travels through this line which is here, then for example, when this change is somewhere in the middle of this line, then on one side of this line you can have, very simply to say, on this one side of the line you can have, for example, logic level high, and on this other half of the line you can have, for example, logic level low. On this one side of the line you will have a different voltage and currents, and on this other side of the line you may have nothing or something completely else. And this is very important to realize, okay? The signal in your board, it travels, it needs some time to travel. That's why I pointed out this part of the presentation. Now, a little bit more from the presentation.
Just for those of you who give a rat's behind. One thing I want to really point out and make clear to everybody, it has absolutely nothing to do with clock frequency. The frequency of a circuit is associated with the rise and fall time. Every single thing that ever goes wrong in a circuit, period, no exception ever in a digital circuit, happens during the rise and fall time. All reflections, all crosstalk, all skin effect, loss tangent losses, all EMI, everything that happens during the rising and falling edge. And the faster the rising and falling edge, the worse the problem becomes.
So, two things what I would like to point out. The first thing, it is very important how fast the change on your signal is happening. So it is completely different situation if, for example, if you are changing your low level signal very slowly to high level signal, and it is completely different situation if you are changing a low level signal to high level signal very quickly. Okay, so when you are changing your signal very quickly, then you may need to take special care. You may need to look at your circuit a little bit differently because there will be a lot of effects. That's exactly, when your signal is changing very, very slowly, then basically you can say that here on this input, it is always almost exactly same voltage as here it is on the output. So you don't really need to consider that the signal will travel through this line. But when the signal is changing very, very quickly, then you will get into situations when here on this input maybe something completely different comparing to the signal which is here on the output. And then when it becomes all much more complicated. And the thing is, all these complications, they are connected with this rising and falling edge, how fast the change is happening. It's nothing about frequency, okay? So even if you are designing boards which are running, I don't know, for example, on microcontroller, if you are designing microcontroller board, you still may need to take special care of the signals because it depends how these signals of the microcontroller are going to change. If they are changing very quickly, you still can see the problems like crosstalk or reflections on your board. You still may see problems like random interrupts on your board, or your board may reset randomly because there is crosstalk between your reset signal and some other signals. And your microcontroller board doesn't have to run on high frequency, but it is using sharp edges. The changes on the signals are happening very quickly. What you will hear next, it may completely change your view at PCB layout. So listen carefully.
And he said to me, except you're looking at things wrong. You're talking about voltage and current. It isn't about voltage and current. Transmission line behavior has nothing to do with voltage and current. We use voltage and current as a measurement tool because that's how we can see basically what the energy is in a transmission line.
So very simply to say, once you start working with very fast edges, very fast changes on your PCB, then basically you will be designing transmission lines. And when you need to have a look at your PCB, at your layout as designing transmission lines, then you may need to not think about voltages and currents. You may need to think about energy, how this energy is transferred through your PCB, how it looks on your PCB. Let's learn a little bit more about energy.
So then he asked me, where's the energy in a circuit? Is it in the voltage or is it in the current? And I thought, and I said, well, you know, in power delivery, you're dealing with a relatively fixed voltage, but you have a very rapid change in current, very high frequency current changes. Sorry. So I said, it must be in the current. And Ralph looked at me politely and he said, no, actually it's neither. And I went, oh? And he said, the energy is in the fields, the electric and magnetic field.
So next time when you will be doing PCB layout, don't forget to imagine the fields.
The energy is in the fields. Then he said, where are the fields located in a circuit?
Good question, eh? How we are going to imagine the fields when we don't know where they are.
Are they in the traces or are they in the planes of the board? Now I'm really scratching my head going, gosh, I don't know. And he said, I'm messing with you, it's neither. He said the energy, the fields, travel in the space between the trace and plane.
Very important, okay? The energy travels in the space between the trace and plane. A little bit more about energy.
The energy in a circuit travels through the plastic and fiberglass, not through the copper. Really? Yes, really. The copper steers the energy.
This is very interesting and very important. So the energy travels through the plastic and the fiberglass on the PCB, not through the copper. The copper steers the energy. So the tracks, what we are designing in the PCB, they kind of guide where the energy or how the energy is going to flow. And if you would like to imagine the fields, this is the picture which can help you. Okay, so this is, for example, our track which we are routing. Here is a reference plane for this track, and these are the fields which are going to be around the track. Now, when you know how it looks, what is going to happen when you move this reference plane further from the track? The field is going to be larger. What will happen when this field is larger? It is going to influence also the other tracks which are on your PCB. All these other tracks, they are going to have also their own fields. All the fields will interact with each other. And that's not everything. When we have these fields very, very large, what does it mean? It means all our board may create all these kind of fields which can be problems during EMC and EMI testing. So what is our goal? Our goal is to keep these fields around the tracks compact, as small as possible. How we can do it? One of the ways how you can keep these fields compact is to have good quality of the reference plane, which is, for example, placed as close as possible to this track. Then these fields are going to be small and compact. Okay, now you understand, once you understand this, then you will see many things will make sense, especially about stack-ups. Yeah, and it really helps you then when you will be doing layout, it really helps you to decide how to place the reference planes, how to how to design the stack up, where you would like to keep a smaller distance in your stack up, where you would like to have a little bit bigger distance between layers in your stack up. Okay? So this is very, very important part from this presentation. The next time when you will be doing PCB layout, try to imagine how these fields are going to look. Here we have an example, okay? This is a track, this is a via, this is reference plane. And basically when you are drawing this track, which is here, you are drawing one part of transmission line. Okay, transmission line is what is used to transfer the energy. What is the other part of this transmission line? What we need to transfer this energy? We also need the reference plane. Okay, so imagine the fields around this track. Imagine the fields which are going to be under the track and also here, between the track and the reference plane. Imagine the situations if the reference plane is not under the track. Imagine the situation, what is going to happen when you are going to change the layers. Yeah, this is one part of the transmission line, this is the other part of the transmission line. That's the way how the energy travels. Suddenly you are going to change the layers. What is going to happen? Let's have a look. Here in this picture, we can see a signal which is routed on layer 1, and then it goes through a via and it continues on layer 3. On layer 2, there is solid ground plane, and let's hear how Rick will comment this situation, how Rick will explain this situation.
Layers, the optimum place to change layers, if you have a ground plane on layer 2, for example, would be to go from layer 1 to layer 3. Why? Where are the fields? Forget the current. Where are the fields in this case? They are in the dielectric space on the signal between layer 1 and layer 2. That's where the fields reside in this transmission line. When you change layers to 3, the fields want to go from that top dielectric space to the dielectric space between 2 and 3. How do they get there? They go through the hole in the plane that we generate when we put a via through the board. Yay, we have a hole, so we have a place for the fields to couple. So the return current couples right through that hole, the fields couple through, creating a return current that goes from the top of the plane to the bottom of the plane. And oh, by the way, just a case in point, if you had 20 ground planes in this board and had a signal at today's rise times, at anything you use today, I don't care what it is, unless it's analog and low frequency, but a digital device at today's rise times with a signal on layer 1, if you had 20 ground planes in the board, all of the return current would be on the top of layer 2. There would be no return current in any of the other ground planes in the board.
Okay, this was quite interesting. So when we are changing the signal from layer 1 to layer 3, and when the layer 2 is the reference plane, then the return current will be on the layer 2. There will be no return current on the other layers even if you have more ground planes in your stack up. Very interesting. Okay, so we understand how this field is going to travel when we are going to change from layer 1 to layer 3, but what will happen if we need to go with the signal a little bit deeper? What will happen if we need to change the reference planes? And that's what you can see here on this next picture. That's what we are going to listen, how Rick is going to explain this situation. Okay, so we are routing a signal from layer 1. Here we are using the layer 2 as the reference plane, and suddenly we continue on layer 4, and here we are going to use the layer 3 as the reference plane. I'm going to play the video.
What this picture is showing is that the fields in the signal on layer 1 are in the dielectric space between 1 and 2. And when you move through a via down to the bottom of the board, in this case, he used a 4-layer board with 2 ground planes on 2 and 3 to do the study. But when you move the signal down to layer 4, the fields have to move to the dielectric space between 3 and 4. How do they get there? By going through the dielectric space between the 2 vias. The fields will couple across the 2 vias. So the closer you can get the return via to the signal via, the better. Now,
what via? This via, which is here. I didn't speak about this via. Do you know what is this via doing? Usually, you will find people call these vias stitching vias. And you will find these stitching vias in the places where high-speed signals are changing reference planes. And these stitching vias, they are ground vias which are connecting different ground planes, the ground planes on different layers. So in this case, this stitching via is connecting the ground reference plane on layer 2 with ground reference plane on layer 3. And the reason why we are placing this stitching via here is so this field can travel between the layers. The field can travel together with the signal. So here you immediately see why these stitching ground vias are important and how they work, why it is important to place them close to the place where this signal is changing the layers. Just to be sure, why we would like to place this via close to this one? Because we would like to keep this field small. We don't want to spread this field around our board. There is one more example which I would like to show you in this video, and it is this situation which you can see here on the picture. This is a layout of a board where signal is routed on layer 1. Then on layer 2 there is plus 5V power plane, and on layer 3 and layer 4 there are power planes which are used to power the driver of the signal which is routed on layer 1. Okay, so this driver is powered with plus 12 volt, which is routed on layer 3, which has the power plane routed on layer 3, and also it is powered with this ground plane, or it is connected to this ground plane which is routed on layer 4. Now listen the explanation, listen this situation, what is happening here. Very interesting.
And I said, there's the problem. And he said, what do you mean? And I said, where's the return current going to be for the signal on layer 1? And he said, well, I attached the thing to ground. I hope it's in ground. And I said, you can hope all you want, but it isn't. The energy is going to take the path of lowest impedance, which is where? Layer 2. And he went, but layer 2 doesn't attach to the driver or the receiver. How's the energy get back to the driver? And I said, there's the problem. The return energy has no direct path back to the driver. It gets back near the driver and goes, uh-oh. And the fields, remember the energies in the field, spread out across the top of layer 1. They find via holes in the plane. The energy won't couple through the plane. A plane offers a 60 to 80 dB isolation factor from one side to the other for energy. So the energy is not going to just couple through the copper unless it's super low frequency. What's going to happen is it's going to spread out, couple through the holes in the copper and around the edge of the copper, down to the dielectric space between 2 and 3, and then create a current in the 12-volt plane to get back into the driver.
And that's everything for today's video. I highly recommend you to watch the whole presentation. It's so useful. even I found some new information in this presentation. How did I find this presentation? I was actually looking at some old Altium Live talks, because again, also this year, I was invited to speak at Altium Live 2019 in San Diego. So if you are planning to go to Altium Live, then we will see each other. Okay, I'm really looking forward to see you on this summit. Okay, what I would like to say is leave comments. I read all the comments which you post under the videos. Maybe I don't answer all of the comments, but I read all of them. And I'm very curious to know what kind of information you found from this video useful, or what kind of information you found in this presentation useful or interesting, or something what was surprising for you. If you like this video, then please don't forget press like button. Don't forget leave the comments, and yeah, everything what I would like to say is thank you very much for watching. Maybe you notice I'm testing new camera. I don't know. Let me know. Did you notice I have new camera? And see you next time. Bye.